you very much. So I'm starting this new chapter, which is chapter 2 for this semester, and this chapter will be followed by another small chapter. They are very closely related to power systems faults and analysis. So this chapter, the title is Symmetrical Components, and this chapter is very important as well as the next chapter that is coming, which will be asymmetrical fault analysis. And symmetrical components is the fundamental that are required for understanding and analyzing power system faults. And when we say power system faults, what do we mean? We mean the faults that occur in power system, like we studied a little bit in power systems 1. We did some tutorial after learning some theories which were basically on three-phase faults, and three-phase faults are symmetrical in nature. But in power systems, we get to see that the faults are classified into two broad categories. One is symmetrical, the other one is asymmetrical. And asymmetrical faults are the major faults in power system, meaning there are a number of faults that occur in a power system. If we divide them or if we classify them in terms of percentage, 5% time you will get three-phase or symmetrical fault. 95% of the time, or 92%, or more than 90% time, you will get asymmetrical fault. And because of that asymmetrical fault, what happens? The system becomes unbalanced. And unbalanced means what? The voltages become different for each of those phases. They are separated by any degree, not 120 degree from each other, which we find in case of a balanced system. And because of that unbalanced system, meaning the voltages are not being the same, the magnitudes of currents will also be different for each of those phases. Now, if we go to the following stage, then we want to calculate the power and so on. Then we need to consider each and every phase separately for their voltage, for the current, for the power, because the voltages are not same, currents are not same for each of the phases. So the powers for three phases will not be same, although the impedances on the load side for each of those three phases are the same, but it's unbalanced because of a fault which is going to cause the system to be unbalanced. Just to rebrush our memory a little bit, balanced system is a system in which we have, if we can imagine a generator that we have, that's where we start, because generators are the sources of active and reactive power, and they also have the terminal voltage where we connect our loads. So if we assume that our generator is ideally prepared or made, constructed, then we will get three-phase voltages out of that generator terminals to be balanced, meaning all the magnitudes of those three-phase voltages will be same, and the three phasors of those three phases will be separated from each other by 120 degrees. So magnitudes are same, the phases are separated by 120 degrees, and then they have a direction of rotation that we will see on the diagram. So if the magnitudes and of the voltages are same and they are separated by 120 degrees from each other, the system is balanced. But in our power systems, like I mentioned, most of the faults are going to cause the system to be unbalanced, meaning the voltage magnitudes will no longer be same to each other for each phase. Also, we might see that the phase angles are changed from 120 degree to any other degree. We don't know what that magnitude and what the angle will be. We can do that only after analysis. So the phase voltages, phase current, powers are different. So that makes our calculation very difficult, meaning we have to consider each and every phase, and it's complicated, time consuming, tedious, all those. So what was done to make it a little bit easy, Fortescue, a scientist who introduced a theorem that is called symmetrical components theorem or three component theorem, that we use in connection with our power system to make our fault analysis easy, especially for the asymmetrical faults. But this theorem is also applicable for symmetrical faults that we have learned in Power Systems 1. So this is such a good theory that covers all the faults, all the asymmetrical faults, and it also includes symmetrical faults. So everything is covered in this theorem that we will learn in this symmetrical components chapter. Then we will talk about the phase sequence, which you know already, but we will just try to remember it because it's important. And then we will come to various aspects such as symmetrical component transformation. We will come to positive, negative, and zero sequence components. We will come to component analysis and synthesis, and then we will go to the symmetrical components of currents and voltages. Then we will consider the general nature of zero sequence currents for various configuration like star connection, delta connection, and then we go look at the power system equipments or the components, like we have series impedance, we have a network, transmission line, we have transformers, star connected, delta connected, and all those stuffs. So we look at all those things, including the generators and the motors that we cannot forget because they are also the major part of the power systems. And that's the last one, is the zero sequence network of transformers is very important. So we cannot afford to not understand any part of this chapter, of course followed by the other chapter where we will do the equations for the asymmetrical fault analysis, but we cannot just make any excuse that we don't understand it, because it's the fundamental of protection analysis, and followed by many other tasks or activities that we do in our power system. And we'll do a lot of tutorials in this chapter. Just to tell you that this chapter has a lot of equation, so you will have to know those equations. We cannot just skip because we don't like mathematics, but these are fundamental. We have to learn this, otherwise we will not be able to analyze them, because it's analysis part. So to analyze them, mathematics need to be understood clearly, right? So let me start with the first one, which is the Fortescue's theorem. This is a theorem that was introduced by this Fortescue scientist. You can see it was in 1918, meaning over 100 years ago, long ago. But it's a very good theorem that is also known as three-component method or theorem, and we use this theorem to apply into our power systems fault analysis for per phase when the system is unbalanced, and the system is going to be unbalanced if a fault occurs in a system which is going to cause the system to be unbalanced. Like I said, that in most of the times we find that the fault happens, the fault that happens in power system is of asymmetrical in nature. The reason is that it's easy. What is the example of an asymmetrical fault? A single line to ground fault. We are always talking about three-phase system and not a single phase system. So three-phase AC system. So single line to ground fault. If we find that any phase A, B, or C is grounded, it's easy for them to get connected to the ground, as compared to all the three phases are connected together. That's a rare chance. All the three phases, they are separated by some insulation. If we are using overhead line, they are separated by a distance, certain distance, maybe meters. But if we are using underground cable or insulated cable, they have insulation, so it's not easy to get them for them to come in contact with each other. So that's why three-phase fault is rare as compared to asymmetrical fault. Single line to ground, double line fault can happen. The chance is little less as compared to single line to ground fault. So double line to ground fault also can happen. So all these faults except the three-phase fault and three-phase to ground fault, which is also of symmetrical nature. So these two faults, three-phase fault and three-phase to ground fault, these two are symmetrical. All other faults, single line to ground, A, B, C, either of them, A, B, B, C, C, A, meaning double line fault, AB to ground, BC to ground, CA to ground is also asymmetrical fault. So they will cause the system to be unbalanced, even though we have started in the first place with a generator which was giving us a balanced system of voltages. So we need this theorem. Now this theorem in general, what it says that if we have an unbalanced set of n phasors, n number of phasors. Phasors means those voltages are represented or considered for analysis and calculation. We represent them as phasor because they have magnitude and they have phase angle. Like we have three-phase system, we label those three phases as A, B, C. Phase A, phase B, phase C. We can also label them as R, Y, B. In some countries they call them U, V, W. So it's three phasors, three phases. So what it is saying in general, an unbalanced set of n phasors can be resolved into n minus 1 balanced set of phasors of different phase sequences on 1,0 phase sequence. Meaning, if we take the example of our three-phase system, these three-phase system can be resolved into 3 minus 1 balanced phasors, in which there will be three phasors, and on top of that it mentions that 1,0 phase sequence system will be there. Now before we go to the phase sequence, 0 phase sequence and all the stuffs, I'm sure that you remember what is phase sequence. What is phase sequence? Can anyone answer? What is phase sequence? You can type if you don't want to talk.
Pattern.
I couldn't hear you.
The repeating pattern.
Repeating pattern is not phase sequence. If you take a square wave, triangular wave, or sawtooth wave, anything, they are also repeating wave, a repeating pattern. I'm coming here every day, 8 o'clock, going home at 4 o'clock. It's repeating pattern. Does this mean that is phase sequence? Does it make sense of what I said? If we say repeating pattern can be anywhere. Winter is coming, then summer will come, rainy days will come. They also repeat, but it's a sequence that we are talking about. So when we have three phase, ABC or RYB or UVW, we need to know which one is coming after which. Like I'm saying ABC, it means A is the first one, then B is following, C is following B. So ABC is the phase sequence in this case. RYB, so RYB is the phase sequence that we mentioned, meaning R is the first one, after that it will be Y, then it will be B for blue, red, yellow, blue. So if we say UVW, U is the first one, then V, and then W. And when we talk about this, it's not just after that it will come. We look at because we're talking about this voltage, so or the current, we know that in an ideal condition it will be of sinusoidal nature. So we should consider a particular point on that sine wave. We can consider positive maximum point, negative maximum point, positive crossing zero crossing point, negative zero crossing point, or any other point, and we have to stick it for all those three phases. So if we say phase A, B, C is the sequence, phase sequence is ABC, meaning if I chose the positive maximum point, meaning phase A will reach the positive maximum point first. After that, phase B will reach the positive maximum point. After that, phase C will reach the positive maximum point. So that's the phase sequence. So which phase is following which phase? Now, as we have three phases as in our practical or real life, ABC or RYB or UVW, we call them. Now, what are the possible phase sequences we can get out of this three-phase system? What are the possible phase sequences? Like we have already said, ABC, RYB. So that's one. Is there any other possible combination that we can get? Anyone to answer? Who can answer?
Yes, so we can have A, B, C, or A, C, B.
A, B, C or ACB? Yes, that's good. Now, apart from ABC and ACB, is there any possibility to get any other phase sequence? Apart from these two, ABC and ACB, apart from these two, is there any possibility of any other phase sequence, if I can say that? Can we get any other phase sequence than these two? Is it possible to get any another phase sequence?
Like negative sequence of course.
Huh?
I don't understand the question.
I'm saying we got two. We said ABC, that is the one that I said after A, B will come, after B, C will come. That's one. Then I asked, is there any other possibility of another phase sequence? Then the answer was ACB, which is right. Meaning, instead of B, after A, C will come. And then followed by, after that it will be B. So SBC and ACB. Is there any other combination? Because we have three phases. So what we see, after A, B is coming, after A, C is coming. So giving us two different phase sequences. Is there any other possibility that we can get another phase sequence? That's what I'm asking.
Sorry, sir.
No, so I don't
Get CAB.
CAB. Okay. I'm writing this. I'll discuss this one. Anyone else? Any other combination that you can just imagine? Just imagine. You don't need to worry about whether it's right or wrong possible. I will explain that.
Yes, I don't think there is any combination that, because if the sequence repeats itself, we'll find the other combination in these two sequences.
Yes. So if we say CAB, I'm putting a question mark. Is that possible? Let's verify. How do we verify? We said CAB. After CAB, what will happen next phase? It will be CAB again. So CAB, CAB, CAB. It will be like that. So if we get to that CAB, 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 and we will find that actually it is ABC. I have, look at the chat facility, meeting chat. I have highlighted. If you say CAB, actually it is ABC.
I understand.
Okay, so we can say CAB, but actually it is ABC. But I can take, so I can write here that it is actually ABC. I can give another example. So I said BCA. I can just think, like I said, just imagine anything. So if I say BCA, what will happen after BCA? First set, another BCA will come, then another BCA will come. And if we look at this, again, actually it's ABC. Can you see?
Sorry, sir. Is that
Is that
where the N minus one comes into play?
No, N minus one, I will go there later on. It will follow from here. I will explain that one. There are a lot that will be coming there. So if I take BCA, it's also ABC. Is that clear?
Yes, sir.
Okay. If I say CBA, for example, so then what will happen? CBA, CBA, it will continue like that. What does this mean? CBA, CBA? Is SCB. Yes, SCB. So what will happen actually? We end up having two different phase sequences, ABC and ACB. There is no other way that we can get another phase sequence. So the first one, ABC, is called positive sequence because we assume it. to be positive. We could say it's negative. It's called positive sequence. And if we change it like ACB, then ACB is called negative sequence. So positive sequence and negative sequence. From now on, we have to remember these two words, positive sequence and negative sequence. Now I'm coming back to this slide that we have from Fortescue's theorem, we have unbalanced system, we have an unbalanced system. And that unbalanced system, according to Fortescue's theorem, has n number of phasors. And what he says that you can resolve this unbalanced system with n number of phasors into a balanced systems, into a set where there will be balanced system of n phasors. So it's not changing the number of phasors, because if it changes the number of phasors, it will be a problem. So that's why it kept the number of phasors or the phases constant, but it is giving us a balanced system from an unbalanced system. And the reason why it is good or useful, because we are useful to balance system and doing the calculation in an easier way. When the balance system is balanced, the magnitudes are same. So that makes our calculation easier. So first step is to get the balanced system from the unbalanced system for the n number of phasors. And from that balanced system, what we get two sets. First one is the n minus 1 balanced system with n phasors and one zero sequence system. And zero sequence system also has n number of phasors. And what is zero sequence system? We talked about positive sequence and negative sequence. The third one is called zero sequence, meaning it's a sequence where all the phasors will have same magnitude, but they are parallel to each other, meaning they will have 0-degree angle from each other. So they have same magnitude for each other and the angle between them is 0-degree. That is called zero sequence because the angle between them is 0-degree. But for positive sequence, negative sequence, they will have also same magnitude and separated by 120 degrees from each other. For positive sequence, it will be ABC. For negative sequence, it will be ACB. Now, if we go to our three-phase system, that's what we are trying to get there. Now we consider three-phase system instead of n phasors. So we have three-phase system, we will have three phasors. So we will get balanced system from the unbalanced system. Three phasors will still be there, and we will get 3 minus 1, meaning two systems that are balanced. One is positive sequence, the other one is negative sequence, and zero sequence system will always be there. It's a constant for the Fortescue's theorem. Zero sequence system will always be there with exact number of the phasors that we start with. Three phasors all the time. We get two balanced system. 3 minus 1 is two balanced systems we will get of three phasors. One is called positive sequence and the other one is called negative system. So we break it down finally like this. We start with an unbalanced system. Because of asymmetrical fault happened in the system, we convert them or resolve them into balanced system of three phasors. From there, we get three set of voltages. First one is positive sequence system having three phasors. Second one is negative sequence, again balanced and having three phasors. The next one is the common one, zero sequence system, in which all the magnitudes of the three phasors are same and the angle between them is 0 degree. So Fortescue's theorem, what it does, it helps us to resolve the unbalanced phasors of three-phase system into balanced systems, from where the equation calculations will be easy. Is that clear?
Yes, sir. Yes, sir.
Okay, so let's go to the next one now. When we talk about this positive sequence, negative sequence and zero sequence, we now need to go to the phasor diagrams and draw them. It will be required for calculation and analysis. Now this is the first one, which is a very common one, which we have been seeing from the very beginning of our electrical engineering, VA, VB and VC, RYB or ABC, whatever we call them. it doesn't matter, but they are of same magnitude and separated by 120 degree from each other if the system is balanced. Now, when we talk about this symmetrical component and try to do the analysis, what we do, we choose a reference phasor. We choose a reference phasor, and the reference phasor is VA, meaning VA is the phasor which is chosen as the reference, and the other two voltages, meaning VB and VC, will be represented in terms of this reference phasor VA. So if we understand that when we talk about these symmetrical components, positive sequence components, negative sequence components, and zero sequence components, what we do, we always use this reference phasor because it makes our calculation easier in step-by-step manner. So what we do, we use the reference phasor, and phase A is chosen as the reference. So VA is the reference phasor voltage, and we express all other voltages in the system with the reference phasor. So VA is the reference, so VA is going to be equal to VA. VB will be equal to something, we don't know it, I will explain that one. VB will also be expressed in terms of VA. So what we see there, A square is there and small a is there. Now when we are doing this phasor algebra and complex number, we saw that in mathematics we use I, sometimes we use J, so A plus IB or A plus JB. So that complex number operator I and J we use is the same. So what happens when we use that I and J operator on a phasor? If I apply the I or J operator on a phasor, what will happen? That phasor will rotate in clockwise, anti-clockwise direction by 90 degree. In this case, A is also such an operator, and it's called complex number operator. And if we apply, let's say we have a voltage V, which is a phasor, its magnitude is V, and its angle is 0 degree at the moment because it's horizontal to the x-axis, so its angle is 0 degree. And if we apply the operator A onto this voltage vector V, it will be shifted by 120 degree counterclockwise, and it will become AV, small AV. And what is the value of A? We'll come to that one. So if we look at this diagram, how we can express VB? VB is where? VB is actually after 240 degree. Can you see after? This is the direction of rotation. This arrowhead there once you see, so it's after after 240 degree, but VC is after 120 degree. So A is the operator which is actually 1 at an angle 20 degree. So when we apply V, when we apply A on V, so V times A, actually it becomes V at an angle 120 degree. That's why this phasor blue one is shown like that, at an angle 120 degree, and its magnitude remains same because it's 1 unit at an angle 120 degree. So VB will be A squared because we apply A, then we get 120 degree displacement. We have to apply another one, so that becomes A squared. That's why this is VB A squared times VA. For VC, you just need to apply the complex number operator once, so it becomes A times VA. So all the times we show the phase voltages in terms of the reference voltage or reference phasor. So we expressed in terms of the reference phasor, which is VA. Is that clear now?
Yes, sir. Sir, could you zoom into your slide?
Oh, okay, I forgot it. The other day you told me. Is that okay? Better now?
Yes, thank you, sir.
Yeah. So that's the first part, reference phasor, and how we express other phases or all the phases in terms of the reference voltage. Now, when it comes to this previous slide, we said we have positive sequence, we have negative sequence, we have zero sequence. Now we have to draw the phasor diagrams according to that. We won't be able to stay with this one. This is a very general one where there was no positive sequence, no negative sequence, no zero sequence. Before today, you never heard of any such thing, positive sequence voltage, negative sequence voltage, or zero sequence voltage. There was only one voltage, VA, VB, VC. But now we have positive sequence, we have negative sequence, we have zero sequence. So the voltages will also be like that. We have positive sequence voltage, we have negative sequence voltage, we also have zero sequence voltage. It can also apply to the current as well. We will have positive sequence current, we will have negative sequence current, we will have zero sequence current. The same thing can be told about the impedance. So far we have had only impedance Z. And now on, we will have positive sequence impedance, we will have negative sequence impedance, and zero sequence impedance. So everything comes in the phasor diagram. We show the voltage, we show the current, we show the R, we show the X. So impedance also now is coming as positive, negative, and zero sequence. Voltage, current, all of them are having positiveness. So all those now need to be shown in the phasor diagram accordingly, so that when they observe that phasor diagram, they can understand what the phasor diagram is showing. Now, this is example of positive sequence voltages. So VA1 is no longer VA. It's VA1, VB1, VC1. Can you see it's VA1, VB1, VC1. So this is showing the positive sequence voltages of this one. This one has all these three. This VA, VB, VC has positive sequence in it. It also has negative sequence in it. It also has zero sequence in it. Because that's what comes from the Fortescue's theorem. So this diagram is only showing the positive sequence part. And how do we know that it is positive sequence part? We look at the suffix here. It's 1. 1 indicates that it's positive sequence. So VA is the phase voltage of A, but VA1 is the positive sequence voltage of phase A. VA1 is the positive sequence voltage of phase A. VB1 is the positive sequence voltage of phase B. VC1 is the positive sequence voltage of phase C. And again, we always represent them in terms of the reference one. Now, in this case, we saw the reference was VA, but in this case, the reference is not VA, it's VA1. Because it's all positive sequence voltages are present here. So VA1 is the voltage for phase A. So we choose the reference for that one, and the reference is VA1. So it has to be VA1, and it has to be VA1 for VB as well. The magnitudes are same. They are displaced by 120 degrees. So when we resolve the unbalanced voltage phasors by using Fortescue's theorem, this is what we get for the positive sequence components, and there we show them in the phasor diagram. So this is the positive sequence voltages for all the three phases, and their expressions are in terms of the reference phasor, which is VA1. Is that clear?
Yes, sir.
Okay, thank you very much. Now if we want to go to the negative sequence, we can check that one. But before we go there, I want to show the complex number operator A. Like we said, I need to decrease it a little bit. Yeah. We said complex number operator A is 1 at an angle 120 degree, meaning when we apply it to a phasor, that phasor will rotate by 120 degree, but its magnitude will remain same, or it will be multiplied by 1, so they will remain same. And it can be expressed in many different forms. We know that we have polar form, we have rectangular form, we have exponential form, all of them are there. So it's 1 at an angle 20 degree, we can write it as like e to the power j theta, theta is 120 degree. We can also write them as cos 120 plus j sine 120. And finally we can get this rectangular form giving us the value of A as minus 0.5 plus j 0.866. That is what we need to remember all the time. So that's the value of A, mathematical expression. Now if that is A, what will be A squared? can do it very easily. So it will be a times a, 1 at an angle 120 degree times 1 at an angle 120 we get 100 and sorry, we get 1 at an angle 240 degree, which can be expanded, and we'll find that it's actually 0.5 minus j 0.866, and we also find it from the observation. Actually it's conjugate of a, because the sign of j has changed there. So a square is equal to a conjugate, and that value is minus 0.5 minus j 0.866. We need to remember these things because it will help our calculations to make it easy. We can skip some steps quickly, and if we go on, we'll find that a cubed will be equal to 1, because it will finally be 1 at an angle 0 degree, because 120, 120, 120, so multiply them at an angle 20 degree, so it will give you 360, which means you have reached the 0 degree of the reference line, which means it's unity. And if you want to know what will be a to the power 4, it will be equal to a, because a to the power 4 is a cubed times a, and a cubed is 1, so that will be equal to a, which is 0.5 plus 0.866. If we want to go on further, we'll find that a to the power 5 will be a square, because a cubed times a squared can be a to the power 5, and a cubed is 1, a squared is a squared is also a conjugate, which you can remember. And then a squared, if we take the conjugate of that, we will get a. And the final one is 1 plus a plus a squared. It's very useful. This is one, is the last one is very useful as well. We will become equal to 0, because we see a is equal to minus 0.5 plus j 0.866, and a squared is the conjugate, so they will cancel each other with that. Minus 0.5 will give you minus 1.0, and then if you add them you get 0. So these are the fundamental properties of this complex number operator a that we use for our power systems analysis in conjunction with Fortescue's theorem. Is that clear now?
Yes, sir.
Okay, thank you very much. So we can go to the negative sequence phasor diagram. For negative sequence phasor diagram, all the voltages related to negative phase sequence will be shown. So VA2, VB2, and VC2. So VA2 is this one. So it's negative sequence. And if we go back to this chat box, when we said negative sequence means ACB. So A is there, so after A, C will come, not B. If we go there for positive sequence, after A, rotating in the direction B was coming, because it's positive sequence, so it's ABC. ABC. So after A, B will come, then C will come, but it's negative sequence, it's ACB. So VA2 is there, after A, it will be C, so it will be VC2. After C, it will be VB. So it's separated by 120 degree, and the magnitudes are same for VA2, V2, and C2. And again, we will express V2 and C2 in terms of the reference, and the reference here is A2, not A1, because it's negative sequence. So we must remember that we link it to the respective sequence. When we are having positive sequence phasor diagram, the reference is VA1. When we're talking about the negative sequence one, the reference is VA2. So VB1 will be now A times VA2, because it's 120 degree. If you operate this VA2 by 120 degree, meaning complex number operator A, you will reach there. And then you apply once again, then you find out that it's actually a squared. So VC2 is a squared VA2. So that's the negative sequence. And for negative sequence, we will always remember when we see 2, then it means it's negative sequence. If we want to write the negative sequence voltage, we must make sure that we use the suffix 2 to indicate that it's a negative sequence voltage. So if I say I2, it's negative sequence current. If I say Z2, it's negative sequence impedance. If I say V2, it's negative sequence voltage, like that. Is that clear?
Yes, sir.
Okay, thank you. So after that, we can go to the zero sequence. Zero sequence is the common one for Fortescue's theorem. No matter how many phasors are there in the system that we are considering, zero sequence will always be there. So for the zero sequence components of voltages, what are the features? I mentioned it earlier. The magnitudes are same. So VA0 will be equal to VB0 will be equal to VC0, and they will be parallel to each other, meaning there will be no phase difference between them, and we use the suffix 0 to indicate that is the zero sequence component. So for positive sequence we use 1, for negative sequence we use 2, and for zero sequence we use 0. So from now on we have positive sequence voltage, negative sequence voltage, and zero sequence voltage. For positive sequence voltage of phase A we will write VA1. For negative sequence voltage of phase C we will write VC2. For zero sequence voltage of phase B we will write VB0. So these notations now need to be very common to us. So just try to remember, it's not difficult. So that's the positive sequence voltage, negative sequence voltage, and zero sequence voltage. Now if we want to go and check what happens with these three sets of voltages. First one is the positive sequence set, meaning we have VA1, we have VB1, VC1. And then the next one is the negative sequence set. We have VA2, VB2, and VC2. Then the last one of the common one from Fortescue's theorem is the zero sequence set. We have VA0, VB0, and VC0. So if we add all these voltages, component voltages for phase A, we will get VA. So if we add VA1, VA2, and VA0, we will get VA. And this addition is not arithmetic addition, it's phasor. So it has to be phasor addition, vectorial addition. Similarly, if we add VB1, VB2, and VB0, we will get VB, original phase voltage of B. Similarly, the same thing can be said for phase C. All the things VC1, VC2, and VC0, if we add them, then we get VC. It does not matter whether the system is balanced or not. It does not matter. If you have VA1, VA2, and VA0, if you add them, you must get VA. If you have VB1, VB2, VB0, if you add them, then you get VB, and VC will be obtained from VC1, VC2, and VC0. Is that okay?
Yes, sir. Yes, sir.
Okay, it's 1:59. Should I continue or let me take 5 minutes? Is that okay with you? 5 minutes? Hello? Can I take 5 minutes?
Yes.
Okay,
Yes.
let me carry on. Yeah, thank you very much. 5 minutes. So this is an example of unbalanced voltages. Like we said, when the voltages or the phasors become unbalanced, what happens? Their magnitudes no longer the same. The phase angles no longer 120 degrees between them. This can be anything, we don't know until or unless we do the calculation. So here I have just a random unbalanced voltages in which VA is very high, VB is little less, VC is the smallest. In terms of magnitude, the angles are very different as compared to 120 degree, but the direction of rotation remains the same. So if we have that unbalanced voltages using Fortescue's theorem, so far what we have discussed is summarized here. So from this set of unbalanced voltages of three phasors, we will have one set which is positive sequence components, VA1, VB1, and VC1. We will have the negative sequence component, this is balanced, VA2, VC2, and VB2, because it's negative sequence, so C comes after A, and this is zero sequence component. So from the set of unbalanced voltages, we will get three sets. First one is the positive sequence, next one is the negative sequence, and the third one is the zero sequence, and that is how we show in terms of notation. We will have to draw this, make sure that you remember these notations, and especially when we have positive sequence A, B, C, when we drawing the negative sequence is A, C, B. And never forget to show the direction of rotations. And for zero sequence components, we'll make sure that we remember the voltages are parallel to each other, or components are parallel to each other, meaning the phase difference or the angle between them is equal to 0. And this diagram is not to scale, but if we want to draw it in to scale, we can also draw it. And the other thing that I was showing or saying, that we can get all the phase voltages if we add them together, like VA1, VA2, VA0. If we add them in terms of phasor, we will get VA, and that is what is shown here. So VA1, VA2, VA0, and this is the resultant. So that is actually VA. Similarly, VB can be expressed here. So VB1, VB2, VB0, and the resultant is this one. You know that polygon theorem. When if you add that one, the last one, then you get the resultant, and that is actually applied here. VB. The same thing is for VC. So VC1, VC2, VC0, and this is going to give us the VC. So this is shown in terms of graphical phasor representation. This is analytical equation. We get the same thing if we draw the diagram to scale. We will get the same answer after calculation. So that's the expressions how we can get the phase voltages in terms of the sequence component voltages. These side, this right hand side, are the sequence component voltages. This positive sequence, negative sequence, zero sequence. This left hand side of the equal sign are actual phase voltages. They are not sequence component voltages. They are like the ones that we knew so far up until today. These are the sequence component voltages. These are the actual phase voltages. So from these we can now derive something that I will discuss tomorrow. But if you have any question up until now, you can ask. Sahil, your question I will answer them tomorrow, because I always used to think that today's lecture, which is of 45 minutes, I want to capitalize that for progressing in terms of lecture, covering the sections and all the stuffs. But for tomorrow it's a long one. We have enough time to discuss them in details. So that's why I will discuss them tomorrow. I remember there were two sections. One was related to the frequency that I told that I will discuss that. And the other one you asked about the question about the harmonics, the sources and all those.
Yes, sir, that's fine.
Today's session, if any one of you has any question, you can ask, don't hesitate. So it's fine if you don't have any question, but make sure that you understand this. And when I'm saying understand, there are a lot of equations I mentioned earlier, and it has already started to show here. But you must also remember that you don't have to memorize these equations. It will come automatically. If you forget, you still can make them. You can write all the equations correctly without memorizing. There is no point of memorizing or remembering these equations. You can write them correctly if you understand the fundamentals coming from the Fortescue's theorem. Three phasors, then we get two balance set. One is the positive sequence, the next one is the negative sequence, and zero sequence is always common. So when you come with positive sequence, is VA1, VB1, VC1, because it's positive sequence, it's ABC, and we show them on the phasor diagram, or when we write the equations, we use the suffix 1. When it comes to negative sequence, is ACB, so the sequence need to be shown VA, VC, VB. So it will be VA2, VC2, VB2, negative sequence. 2 is for negative sequence. And when we go for zero sequence, so it will be VA0, VB0, and VC0. So the voltages can be obtained by the sum of the three components, positive, negative, and zero. That is what is shown here. A phase voltage can be obtained by the addition of all the three components that we resolved from the Fortescue's theorem. Fortescue's theorem helped us to get these three components positive, negative, and zero. Now we have them. If we add them together, we'll go back to the original. That is the fundamental that is shown or selected here on the slide. That is what you see. If you have VA, VB, BC, balanced or unbalanced, you will get VA1, BB1, BC1, VA2, VB2, BC2, VA0, BB0, VC0. Now, when you have VB, all these 9 parameters there from 1 to 0 from A to C, if you add them correspondingly, you will get the 3 phase voltages for VA, VB, and BC. Is that clear?
Yes, sir.
Okay, thank you very much. So we'll continue tomorrow.